So let's start with classical computers. Start with theorems and proofs in mathematics. How do you prove theorems and how computers can help us? Probably most of you have heard about Fermat's last theorem. This was stated almost 300 years ago, that that equation above, this equation, doesn't have any solution for integer numbers, for any. This was stated by Fermat. And people tried to prove this and couldn't. People tried to disprove this and find a conflict. They couldn't. But they came up with partial proofs. So they proved that this theorem is true if n is 2, it's obvious. Not n greater than n, because for n equal to 2, it's Pythagorean theorem. They proved that it's not true for 3, which is odd number, and prime number. They proved it for 5, 7. They came up with exact proof. But they wanted a proof for any, so they checked and they developed a theory and proved that it's true if n is less than 4 million. They proved for all prime numbers less than 4 million. But they couldn't come up with a complete for any. It took 300 years that Andrew Weiss in Princeton proved this theorem for any n. So that's why mathematical proofs are very difficult. Then you can ask why people bother themselves so much to prove it if they have arguments and evidence and proofs for these many, many numbers, why they do not just trust this conjecture and state that this is true for everyone, because they have checked many, many numbers. So any mind almost immediately will come to this conclusion that this theorem is general. Let's see why. Why mathematicians are so peculiar. Let's take another example, the Goldberg conjecture. He conjectured that any even number can be written as the sum of two prime numbers. For example, 20 is an even number. It can be written as 13 plus 7, two prime numbers. 24 can be written as 13 plus 11, two prime numbers. 46, the same. And then you can check these conjectures for many, many numbers. And it has been checked for up to this number. It's a very huge number. You know that conjecture of Goldberg is true up to this number. And if you check it today, probably this number has been larger. But again, Goldberg conjecture has not been proved or disproved. If you prove it, maybe you will earn the $1 million prize of the Clay Foundation. It's an open problem. Then we can ask why people do not trust Goldberg conjecture. Why they do not state that it's true. Let's see why. Again, another example. This is the Euler conjecture. It's similar to the Fermat. It says that this equation, x to the power 4, y plus 4, z plus 4, equal to w to the power 4, it doesn't have any solution for integer numbers. This is the conjecture of Euler, almost 300 years ago. And it was true. It was checked for many, many numbers. But then, suddenly in 1988, a counterexample was found. It's not true for these large numbers. You can imagine why it has been so difficult to disprove this, because these numbers are very large. And still, it contradicts the Euler conjecture. So you check it for small numbers, and you are happy with that, but then when you come to larger and larger numbers, at some point, you will find a counterexample. And then it means that you cannot trust the Euler conjecture. Right? Another counterexample. People knew that these numbers are prime. 3 and 1. 31 is prime. Then you add more 3s. 3, 3, 1 is prime. You can check it. 3, 3, 3, 1 is prime. Again, you can check it on your computer. And then you come and add these 3s. You think that it's true, but then you will find that at this number, it's not true. If you have 8 of zeros and 1, 8 of 3s and 1, it's not a prime number. It's a multiple of these two numbers. Right? And then, the most striking example. Try to count the number of prime numbers between 1 and 100. Right? You will find 25 prime numbers. 3, 5, 7, 13, 11, and so on. There are 25 numbers between 1 and 100. Then you move this interval to higher numbers and try to find the number of prime numbers between 1000 and 1010, or 1100. You'll find 16. This number is wrong. 1100. You will find 16 prime numbers. Between 1 million and 1,100,000, you find only 2 numbers, 2 prime numbers. And then Gauss found a formula for that. The formula is this. The number of prime numbers less than n, he conjectured to be true, truly given by this number, n divided by logarithm of n. This is the number of prime numbers which is less than n. Or more accurately, the number of prime numbers less than n is given by this. More accurately because he added these small numbers here. And this is a very close approximation to the number of prime numbers. In fact, it's an upper bound. If you count the number of prime numbers less than n, the exact numbers are these yellow dots. And the Gauss formula is this smooth curve. And you see that it's a correct upper bound. The Gauss formula is always above these numbers. So it's a true number. It's a true theorem. It's a valid mathematical statement. Number of prime numbers less than n, as given by that formula, pi over log of n, given by Gauss formula, is a valid upper bound. It's valid up to number 1,000, 10,000, 100,000, 1 million. Right? So you go up.
Right?
Yes?
Shouldn't that be an increasing function?
Sorry?
Shouldn't it be an increasing function, the number of prime numbers?
No. Yes, it should be. Yes, this is the interval.
And the interval.
Yes, it is the interval. Sorry. Yeah, you were right. And then you check this. Thank you very much. And then you go to larger numbers. 10 million, 100 million, 1 trillion. It's still true, right? This is the density. And then, naturally, you have to trust this further because it has been checked up to this 1 trillion number. And then, it came up with Stanley skews for counterexample. He found that after this number, 10 to the power of 10 to the power of 43, the formula breaks down. It's not true after this number. Note that this is not 10 and 43 zeros. It's 10 and 10 to the power of 42. If you write this, the number of zeros will go around the equator many times. It's a very huge number. But after this number, the formula of Gauss breaks down. It's not true after this number. So we understand why mathematicians need proofs. Why they take so much trouble and spend their life for proving a simple formula, which every school children can understand, but many generations of mathematicians should spend their lives to prove this thing, because counter examples are not enough to prove it. So in 1900, in the mathematical context, David Hilbert, the famous mathematician, posed this problem. Can we solve these problems by algorithms? A problem like this is one of these examples of Fermat theorem. He asked this question, can we solve these problems by algorithms? And at that time, there was no computer, so the concept of algorithm had to be formulated. And he meant that by a finite number of mechanical steps, by repeating those steps, can we prove or disprove these theorems? This was the basic formulation of Hilbert problem, the famous 10th problem. You give me a theorem, and then I have a number of statements, a number of finite steps, a finite number of steps, and go these steps one by one and repeat them if necessary, and then I will give you the proof of this theorem. Or I will tell you that this theorem is correct or not. This was the statement of the 10th Hilbert problem. So this is the definition. A finite sequence of operations which can be repeated mechanically to solve a problem. Let's try to formulate a couple of simple algorithms to see what Hilbert means. Some examples. Suppose that we want to determine if a string of zeros and ones has an even length. Even length means, for example, the length is 4 or 1,000 or 10,000 and so on. For small numbers, we can count by our eyes. But for large numbers, for large strings, we need an algorithm. We cannot go to thousands of digits and decide whether the number of digits in this string is even or odd. We want an algorithm. And the algorithm is very simple. In an abstract way, you can think of this. You construct a machine. It doesn't matter how you construct this machine. Maybe it's electrical, maybe it's optical, maybe it's mechanical. And it has two states. Q even, which is the starting state of the machine, and an odd state. And you give these digits to this machine. The string enters the machine. And the machine's state changes one by one. If it receives a 0 or 1, it goes to the odd state. And another digit, regardless of whether it's 0 or 1, brings it back to the Q even state. You can think of the Q even as a green lamp and Q odd as a red lamp. Originally, the machine is in the red lamp. And then it receives the digits, and then it goes on and on. And this is the mathematical way of writing this. This is a transition function. If the states of the machine is Q even, and it receives anything, it goes to Q odd. If it is in the Q odd state and receives a digit, 0 or 1, it goes to the Q even, it comes back. And now this machine can recognize any string, no matter how large that string is. You give the string to this machine. It loops around, and starts somewhere. At the final stage, if the lamp is green, you will tell that the string length is even. If it's red, you say that this string has been rejected. The length of the string is odd. And then you can go on and design different algorithms and solve more complicated problems. For example, the example 2 is this one. Determine the strings whose length is a multiple of 3, right? Then you have just to add a single state to the states of the machine. The machine has now 3 states. Q0 is the starting state. If it receives a 0 or 1, it goes to the Q1 states. Another 0, 1, it brings it to Q2 states. And then it goes to Q0, the green line. And then this string, or this machine, it's very simple in construction. It can decide whether a trillion-digit string has an even length or odd length. So you have solved a very complicated problem by a simple algorithm, by a simple machine, right? You may say that these examples were quite simple, but then you can try to solve a more complicated problem. Example 3. Determine the strings which contain 0, 0, 1. So you have a very long string, and at some point in between, there is a substring 0, 0, 1. You want to see if your string contains such a substring, right? 0, 0, 1. Then you can, of course, imagine more complicated strings. Let's design an algorithm, a machine which distincts, which recognizes this type of string. It's a little bit more complicated than the previous one. So, should this string be accepted by the machine or not? Yes or no? No. How about this one? How about this one? Yes or no? How about this one? Yes. But note that this substring may be hidden among thousands and thousands of strings. And we want to design an algorithm for finding this. And the algorithm is this. The machine is this. So originally you are in the Q started state. You receive 1. You do not go ahead. Why? Because you are waiting for a 0. Right? The moment that you receive a 0, you go up. You come to this Q0 state. If you receive now one digit, you come back because you want 2 consecutive states. So if you are in the Q0 state, you go up to Q00 state. More zeros will loop here, and another one will bring you to this Q001 state, and you stay there. The green lamp will do. More zeros than 1 doesn't care, because you want one substring. So a more complicated problem has been solved by a slightly more complicated machine. And then at this stage, you are very happy. Why? Because you tell that I can solve any problem with any machine. I just make more complicated machines. We just add more states, more complicated diagrams. In just 3 or 4 states, we solve this problem. But you can design a machine with 1 billion states. Then you can solve any problem. Not 1 billion, just 5 states, 6 states, 10 states. Then you can solve more complicated problems. Can we solve any problem? Yes or no? By the tone of the question, you can say no. You cannot solve this simple problem, right? The problem is this. We want to determine whether a string is of this form. A number of zeros and an equal number of ones, right? We want to see if a string has a number of zeros and an equal number of ones after that. Such machines, no matter how complicated they are, they cannot solve these problems because they have, in the spirit that I explained the problem in the previous slide, they need to store the number of zeros and then to decide whether the number of zeros which has been detected is equal to the number of ones that are coming up. So they have to have an infinite memory. And no machine, no finite machine has an infinite memory. So no matter how complicated you make your machine, no matter how complicated the state diagram, no matter how complicated the states are, you cannot solve these simple problems. At this stage, you can say that we cannot solve mathematical problems by algorithms, right? And you can say to Hilbert, we have given a negative answer to your question. But Hilbert may tell you that we have not made the most concrete or the smartest algorithm, the smartest machine. Somebody may come and make it more complicated, and from basic principle, somebody may come to make a more complete definition of algorithm. These are just simple machines. And this was done by Alan Turing, a famous guy. Almost all of you have heard about Alan Turing. He is now an inventor of modern computers. Also at that time, there was no computer, he just wrote the theory of computers. And what is the steps of Alan Turing argument? Tell you that how do we human think? We have a mind, and our mind has a number of states. We have the states of mind, and we have an infinite amount of papers. We write on the papers, we read from the papers, and then according to what we read, the state of our mind changes, and depending on what we read and what our state of mind is, we write on the paper. This is the argument that the type of thinking that we humans do, right? We write something, our state of mind changes, and we write another thing, right? And then we go on and develop proofs, develop theorems, develop calculations, and so on. But we want to make these diagrams, into an abstract thing. And this was done by Turing. And the abstract machine is like this. You do not need a huge stack of papers, two-dimensional papers. The papers can be just one-dimensional. And you do not need English or Persian or Turkish alphabets. You just need zeros and ones. So the zeros and ones are written on a single tape of machine. This is the tape. This is the starting state. And there are a finite number of states in this machine. This is the brain of the machine, brain of the computer. And this is the head. And this head moves back and forth and reads from this paper, this tape, and writes on this paper. So this is the whole mechanism and the whole process of our thinking and the process of any machine. You read these zeros and ones, the state of the machine changes, and then you change the digits that have been written here. So this is mathematically, in an abstract way, written in this form. Q is the state of the machine. S is what is written here. And this is the transition function. You write Q prime, because the state of the machine changes, depending on what you read. You write as prime because depending on what you have written, and what is the state of the machine, you write something else. And what is this plus and minus for? Who can guess what is this plus and minus? Just to wake you up.
Review.
Sorry?
Review.
The movement of the head, almost correct. It decides that the head goes right or left. Right? This is the mechanism of this machine. So let's try to solve some problems with this machine. I want to solve this very simple problem. Given any string, the input can be any string. I want the output to be just one. I want to change everything to one. Right? How this machine works? Very simple. At the start, the machine is here, the head is here, and the state of the machine is Q start or Q sub S. Right? It moves here, given by this formula. It goes right. Right? Sorry, these zeros and one are not shown here. It's a problem of converting Keynote to PDF. Some of these notes, some of these fonts disappear. Anyway, I explained here. If you find a 0, we change it to 1. If you find 1, we change it to 1. And you go forward and forward and forward. Until you reach a blank cell. When you reach a blank cell, you stop. This is the working of this machine, which is very simple. Another example. Convert 0 to 1 and vice versa. We want to convert any string so that any digit 0 becomes 1, any digit 1 becomes 0. Again, you do not need these slides. You can just try to solve this on your own paper and define the transition functions. I have written them here, right? If you read a 0, you change it to 1 and go forward. If you read a 1, you change it to 0 and go forward. If you read a blank, you go to the state QH, which means Q halt. The machine stops and do nothing. It doesn't. It's not important to go forward or backward. The most important thing is this Q halt. You stop and the work is done. Again, these numbers are not shown here. Now you ask, is it possible to solve the previous problem that the finite machine couldn't solve? I want to see if our Turing machine can solve this problem, to recognize the strings which have equal number of zeros and ones. Now you can prove, again, I leave it to you because these numbers of zeros and ones have disappeared. You can solve this problem, which was very complicated for the previous machine, by this kind of machine. You just sweep around. It's a very beautiful algorithm. You can read it here. And you can solve this problem by this type of machine. It's quite simple. Sorry. I try to put back the zeros and ones and leave the slides here if anybody wants to check it. I have animated all these movements here, but unfortunately it's not possible here. Okay. So the universal Turing machine, which is the mother of all these computers that we have, is a machine, and it has a tape, and this tape, on one part of it you write the program, and the other part you write the data. And all of these machines that you see, no matter how small or how large they are, supercomputers, anything that you see, is based on these Turing machines. The Turing machine can simulate and can reconstruct everything that you see in the modern classical computers. And the name of this is the Church-Turing thesis. In fact, these two people prove that anything that can be solved by algorithm, anything that you can imagine by algorithm, no matter how complicated they are, can be solved by these Turing machines, right? So the Turing machine is the ultimate concept of the algorithm that we have. We do not have anything more complicated than Turing machine and more powerful than Turing machine. Any problem that you can solve, any function that is computable by algorithms can be computed by Turing machine. Now, the Turing machine may seem complicated. It has been shown that it can be modeled by something which we call classical circuit. What is a classical circuit? It's just a sequence of logical gates, like AND, OR, NOT, and so on. You have a number of digits here, a number of bits, classical bits, zeros and ones, and then you have a classical circuit. A classical circuit is something like this. It is a huge collection of different gates, right? Again, these gates are logical gates. It doesn't matter that you make these logical gates by optics, or by water pipes, or by sound, or by anything. The logic is the same, right? Maybe in the future, we get rid of all these electronic gates, and we come to use optical gates. The logic doesn't change. So this is the classical circuit. Nowadays, they make these circuits by electronics, but it may change, right? So the circuit implements the Turing machine, not completely, because after all, the memory of these chips is finite. It's huge, but it's finite. The tape of the Turing machine is infinite, but it's a very good approximation. Now, let's go back to the question of David Hilbert. Can we solve, oh sorry, you saw the answer. The surprise went down. So, let's deal with this one. Can we solve any problem by algorithms? We go back to the question of David Hilbert. Can we solve any problem by algorithms? Any mathematical problem? Can we prove mathematical? What is the answer? It's no, you can't. Still you can't. Is it just a matter of our deficiency of competence? So we can have more complicated and more advanced computers in the future, in the year 3000, for example, to solve mathematical theorems and prove theorems by computers. Can we solve it or not? Is it a matter of principle or just a matter of technology? What is this? It is a matter of principle or technology. It's a matter of principle. In fact, Turing showed and proved that it's not possible. You can't. And how? In fact, I don't know how much time I have. I have plenty of time. Okay, but I will end my lecture soon. But I can probably go and prove it. It's called the halting problem. In fact, Turing proved that it's not possible, no matter how complicated your Turing machine is, to prove mathematical theorems. The argument goes like this. It's called the halting problem. It can be formulated in many different ways. The simple base is this. We have many softwares, right? Many powerful softwares, many powerful computers. You can ask yourself, Is it possible that I have a program, I write a very powerful program, and I run it on a very powerful machine, a supercomputer, right? And then the job of this computer is that it tests, it verifies the logic of my program, the logic of my proof. Is it possible that this computer does this thing? So you have an input, and you have an algorithm. You give this to this huge machine, which is called test. And the output is that either it accepts this string, it says that this algorithm stops on this input. This is one outcome. The other outcome is that the machine, the test, loops and loops and loops and never stops. Is it possible to design such a machine? Let's look at it again. So we have a machine which is called test, right? And then the input is a number, for example, a huge number or something like that, and an algorithm. And the algorithm wants to decide whether this input, this string, is accepted by this algorithm like the ones that we described in previous slides. And the green lamp shines, or no. The machine loops and loops and loops. Doesn't stop, doesn't halt. That's why it's called the halting problem. So this is the statement of the problem. Does the algorithm stops and the given input loops forever? Let's formulate this in a more familiar way. You give the machine a theorem, right? Like the Fermat theorem. And the proof that you have tried and worked out on your paper, you have spent 1 year or 2 years, and then you have come up with a proof of the theorem. It has many lines of arguments, right? And you give this computer the theorem, the statement of the theorem, and the proof that you have written on the paper. And you ask the computer, is your proof correct or not? Right? The computer wants to check the validity of your proof based on the axioms of that theorem. Right? So the computer should check the lines by lines of your proof. It should check the theorem and the axioms that you have used. And it wants to check whether you have made a valid argument, whether you have made a mistake or not. And the halting problem, the halting theorem of Turing, states that this is not possible. You cannot make such a machine. By principle, you cannot. So it's a good news for mathematics. It means that it's a good news for human mind. It means that nothing can substitute the human mind. There is space for creativity of the human mind. There is space for mathematics. There is space for argument, for logic, for science. Not all of sciences, not all of our human processes, thinking process can be delegated to computers, right? It's a matter of principle, not a matter of technology and speed. If you want to prove, if you have the patience, it's a 3 slides. Okay, shall we go with the proof? So, I skip these 2 slides and then come back. The proof is quite simple, and of course a little bit demanding. The basic part of the theory, of the proof, is that Turing proved that every Turing machine, no matter how complicated, is defined by a number, a natural number. So any Turing machine has a unique number. Maybe you make a Turing machine which is very complicated, and it is the Turing machine number y. Y has 10,000 digits, 1 billion digits. But principally it's possible. This is the basic part of the Turing. So any Turing machine which is my, has a unique number. The Turing number, machine number 1, Turing machine number 2, the Turing machine number 1000, Turing machine number 1161, etc. etc. All these machines are ordered by their numbers. Any input is a natural number. Sequence of zeros and ones is coded in a natural number. Now the halting problem, the test problem is this. Does this test machine stops if you give the input x to the machine my, right? Does it stops or it loops? Does the machine y stops and the input x? This is the question, right? If such a machine is possible, suppose that such a machine is possible, then we come to the contradiction. The contradiction is this. You put this into a larger machine. In principle, you can. You define a larger machine, you call it hold m sub h, right? And the definition of this machine is like this. It gives an x, it gives an y, so these are the inputs, the same inputs into the test machine, and then if the test machine halts, the MH machine, the halt machine, stops. If it stops, it goes round and round and round. Right? And now you make a slightly different machine. You give this the same machine, but you give the input H. And now you see the contradiction. On the input H, if MH stops on H, right? MH loops on H. If MH loops on H, then again MH stops on H. This is the contradiction. Again, this was our original machine with two inputs, x and y. X is the input, y is the number of the algorithm. It had to verify whether my stops on x or not. Now we have given the test the same numbers. H, instead of x and y, I have given h and h. And this number comes to a contradiction. Here you see the contradiction. If mh stops on h, which is this one, again mh loops on h, and vice versa. This means that such a machine is not possible. I leave these slides here so that you can contemplate on this, because it's not so easy to grasp. It has been formulated by many other mathematicians like Bertrand Russell. And then you can also find these similarities with this famous theorem of good. Probably you have heard about Kurt Gödel, the great mathematician and logician, who proved that in any axiomatic system, no matter how complete they are, you can always find undecidable theorems. Theorems which cannot decide whether they are true or false. In any axiomatic system. No matter how you complete your axioms, you add axioms so that they are complete and you can decide about the validity of the mathematical system. You can again find and construct mathematical theorems which are not decided. So what we have found is that in this lecture, we have found that what is a classical computer is nothing but a Turing machine, just made by wires and transistors and so on, but the logic and the design is the same. It's the most complete formulation of algorithm that we have. No one has come up with a more complete and stronger formulation of algorithm than the Turing machine. The Turing machine, in this sense, are very powerful. They can solve any problem which can be formulated as algorithm, but they have limitations. They cannot solve the halting problem. They cannot solve any problem. It means that there is still space for creativity of the human mind. There is still space for mathematical and scientific reasoning. And then, in the afternoon, we see in this context what is a quantum computer. So, with this, I stop here. Thank you very much.